Hi, Bobby.
Hi, Ani. So, shall we charge a capacitor and discharge through an inductor and see what happens?
Sure, let's do that. We need to work on more complicated
Correct,
problems, no?
correct.
We started this because we wanted a higher order differential equation.
Yeah.
Let's do it in the Laplace domain and see.
Yeah. So, let's say we have a capacitor which is charged to some voltage already. So, what I have is a capacitor plus minus 1 volt. Already it is just a charge, and it's a 1/2 farad. This is going to a switch. A resistor and an inductor. Something like this. So, this is 1 Henry and this is 2 ohm. And the switch is initially open.
Okay.
We are closing at t equal to 0.
Okay.
So, basically the switch is operated using u of t.
U of t. Correct.
When u of t is high, switch is closed, otherwise open.
Okay.
So, question is what's the current going through?
Okay. You want I of t.
I of t.
Okay.
So, since we are comfortable with Laplace transforms,
let us do that.
The entire circuit will transform to...
Yes, because I can already see this will give you a second order differential equation.
Yeah.
Because capacitance current is C dV by dt.
Yeah.
And then the inductor voltage is L di by dt.
Correct.
Which means the inductor voltage is the second derivative of the capacitor voltage or something like that. Right. So there is clearly it's going to be a second order differential equation.
Yeah.
Let's go to the Laplace domain.
Yeah.
And then the students will see how easy it is to solve it in the Laplace domain as long as you do it correctly.
Correct. So, yeah, it looks, although it's simple, it looks complicated also because capacitor will discharge to this.
That is true.
So, that current will charge. I don't know. Let's see what happens. So, let me try. The capacitor, if it has a initial charge, that will become initial voltage, that will become a voltage source by
yes. CS. Correct.
Yeah.
Correct.
CS or just S? I think C got cancelled, I think.
Correct. That's right. It is just by S.
Yes.
Correct.
So, plus minus.
It is the initial voltage by S. Correct.
Then the capacitor, we will write it as 1 by CS, no?
1 by CS.
1 by CS.
In this
so,
case, it is,
here it is
2S.
Yeah. So, 1 by 2.
1 by 2S, correct.
Okay, then switch is closed. I have. Sorry.
Resistor is a resistor.
Yeah. 2 ohm. Then the inductor, anyway, there is no initial condition.
Correct. The switch is open.
Open.
So, there is no initial condition.
And this is
SL.
SL.
So, S.
Because L is 1 here.
Correct.
Oh, it's so simple, no? I was expecting something complicated. Because the initial condition is captured here.
Correct.
Okay. So, I of S. Correct, no?
Yes.
Let's try it. So, I of S is equal to 1 by S is the
voltage.
divided by just the total impedance.
Correct. Sorry,
Ah,
1 minute.
something
This
wrong?
is 2 by S, I think. It is 1 by CS, the capacitance impedance.
So 1 by
CS.
CS.
So, and C is half.
C is half.
Correct.
Okay.
So, it will be 2 by S.
So 1 by 2S.
Correct.
2 by S. Yeah, correct. Thank you. 2 by S.
Correct.
So this is 2 plus 2 by S plus S.
Plus S.
So we can, so S and S may get cancelled.
Correct.
So S square
Plus 2S
plus 2.
Yes.
Okay. Oh, now what we will do?
Okay. We need to find, try to make this
Into some
usable, well, eventually we want to find out I of t,
correct.
which means we need to take the inverse Laplace transform.
Correct.
We need to bring it to something that we know.
So if it is
Some
1
form.
by S plus something, etc.,
1 by
then
S
we
plus
know.
A, 1 by S we know, 1 by S plus A we know, something like that we have to do. I think we did one problem where we split it into partial fractions.
Correct.
Right?
Correct.
Something like that we have to do.
Oh, so here, so this means I can write it as maybe S square plus 2S plus
1 plus 1 maybe?
1 plus 1. Yeah.
Okay.
So this will become S plus 1 whole square?
Correct.
Okay.
Okay.
Yeah, if this 1 was not there, it would have been easy.
Yes. It would have just been 1 by S squared plus 1.
Yeah. Or it is like omega by S
squared plus omega squared. Correct.
Where omega is?
That is just sine omega t.
Sine
There's
omega t.
omega is 1, so
Correct.
sine t.
Correct.
Okay. So now,
But this seems to be something more.
okay. See, we saw what happens. Okay, I see. So we need to find out what corresponds to this. No? Some property we need to see.
Yeah.
Because yeah, we have seen so many properties, no t, but none of them seem to be applicable here.
Correct.
Huh?
So what we are saying is we have omega by S plus A whole square.
Plus omega square. Correct. That's what we have. Correct. So it looks like instead of capital F of S, we have capital F of S plus 1, something like that, or a capital F of S plus A. Something like that. Is that correct?
That's true.
Huh? Something like that.
Okay, so what you are saying is it's omega by S plus A
whole squared plus omega squared.
Omega square.
Right? So it looks like instead of S, we have S plus A.
That's true.
Right?
What could... Okay, maybe we can refer to the list of transforms.
Yes, I think there is one more transform. Just like, I think there is a transform that relates the S plus A.
So whenever there is a S plus A or S minus A, usually there is a...
correct. So what we noticed is there is some exponential related to this, correct?
So, of course, I was checking this textbooks.
Okay.
So, if you have, I think, e power minus at.
Minus at, correct.
Let's say sine omega t. Or in general, e power minus at f of t.
F of t, correct. Then let's write down the Laplace transform for this.
Whether we will get, we can check.
Correct.
So this will be, I mean, f of s will be integral 0 minus to infinity f of t e power
minus at
minus
into minus st. Correct.
Correct. So s plus at
Correct. Correct.
dt.
Ah. Okay.
Oh, what is this? So is this equal to?
Correct.
I mean, s has changed to s
Correct.
plus a.
Actually, this is not f of s.
Hmm.
F of s is the Laplace transform of f of t.
Ah,
So we can't write f of s here.
okay.
So this is just the Laplace transform
I
of
will
that.
write the Laplace transform of,
Ah, correct. That is better.
yeah.
Correct. Correct.
Now it is accurate. Yeah.
Correct.
So Laplace transform of this is this.
Correct. And now this is capital F of s plus a.
Okay, okay, okay.
Right? If we had capital F of s,
Ah,
it would be
I would have written f of s.
correct.
I mean, if it was just
E power minus st.
correct.
But now it is e power minus s plus a into t. So wherever s was there, it is replaced by s plus a.
Okay, okay.
So that is just capital F of s plus a.
As far as the integration is concerned, it doesn't know whether
doesn't
it's s
know.
or s plus a.
Correct. And after all, the Laplace transform, as we learned, right, it's a mathematical technique, no? To map the time domain function to something
To
else.
something else.
So the mathematics clearly tells you.
Okay, so that means we are somewhere close to the answer.
Yes.
So then the time domain thing for this.
Well, maybe what we can do,
Ah.
we can write f of s plus first.
Ah.
So if you did not have the 1 here, if you did not have the a, we know that is sin omega t.
Sin omega t.
Right? So if you have a,
Ah.
then it is e power minus at sin omega t,
Correct. So here it's I of t.
I of t. So e power
So what
minus
you are
at,
saying is, if 1 was not there,
correct.
it would have been sin
Actually sin t, here
sin
omega is 1.
omega t. Omega is 1.
It would be sin
Sin
t,
t. U of t
u of t.
ampere.
Correct.
Now this 1 is there. That means s will have a,
Correct.
I mean, s had a
Plus 1
plus 1. So that means there will be an e power
minus 8.
minus at. A is 1 here, so minus
E power minus t.
t.
Correct.
Okay, okay, okay.
This is actually quite interesting. I don't think we've ever seen a function like this before,
Yeah.
right? So maybe we can quickly plot it to let the students understand. So it looks like at every point we are multiplying the sinusoid
With the exponential.
with an
part.
exponential, right? Maybe we can
In a fresh page.
in a fresh page. So maybe we can draw the sinusoid first,
Yeah.
draw e power minus at first,
Yeah.
we will multiply the two.
Sinusoid approximately I will draw. Will be something
Sure.
like this.
Correct.
Here it is, height is also 1. E power. So P, amplitude is 1.
Amplitude is 1. E power minus at at t equal to 0 it will be 1.
Yeah.
T equal to infinity it is 0.
0. So it will
is
be
exponential, right?
exponentially decaying.
Decay.
This one. So again from 1.
Correct.
Not very accurate, but,
But
it will
yeah,
be something like
it
this.
will be something like that.
Oh, and then we are multiplying these two signals.
These two signals. So we can draw an approximate. We can never get an exact one.
Yeah.
Approximately we will draw.
If there was a tool, then we could have used
Yes.
that.
But what I'm thinking is, it looks like, see, e power minus t represents the amplitude of the sinusoid. It looks like the amplitude of the sinusoid will reduce over time. That's what it seems like to me.
Exactly.
Right? Earlier you said amplitude sinusoid has 1 in the first curve.
Yeah.
That is just 1, right? It's
Yeah.
amplitude of 1 forever.
Yeah. So maybe I will draw a slowly decaying.
Slowly decaying 1
So that
exponential.
my drawing will become easier. something like this.
Sure.
So which means by the time I reach here, it should be 0.
Correct.
Okay, let me try. Going to be bit,
So yeah, correct. And the next one will be smaller and
Something
smaller
like
and
that.
something like that. Correct.
yeah.
And each one of these is not half a sinusoid because continuously at every point,
Yeah,
right? But
yeah.
but I think the students get the idea.
Yeah. So this is our I of t.
Correct.
So the capacitor has transferred some charge to the inductor.
Correct.
So there is a current flow, then the capacitor.
That's right.
So-
Actually, the current is going negative
Correct.
because the power is being dissipated on the resistor, only in the
because that's the
resistor.
only component where there will be power loss.
Power loss. Because if the current goes to 0, there is no power in the system, there is no energy left
So finally, there will be some heat coming from this resistor.
coming from the resistor. And I can see in the process it has to pass current.
Hmm.
It is charging the inductor. Now the inductor has energy, is going to try to send it the other way. So the current is becoming negative.
So if this resistor was not there,
Okay.
then e power minus
Ah,
1t.
well, let us see where the resistor is coming in this picture. Shall we solve this? I of S.
Yeah,
Huh?
it will be, this
That
2
portion
will
will
not
be
be
gone. And so you will get 1 by s squared plus 2.
I can write it down.
Yes.
So this is we are just trying out what happens.
Correct. So no resistor, no 2 ohm resistor.
Yeah. If R is 0, then what happens to
Yes.
this?
Correct.
So this is 0. That's what
This
we
will
are
go to
saying.
0. Correct.
So
1 by s
1
squared plus 2.
by s, 2 by s plus s. So 1 by s plus.
Oh no, this 1 by s will be gone.
Correct. This s and this l will get
Correct.
cancelled.
Correct. This we know. It's a sinusoid,
Okay.
right? So we just saw that omega by s squared plus omega squared.
Omega square.
But the omega is different.
Yeah. It's not. Did we make any mistake?
No, I think
No.
this is right.
Okay.
This is correct. The omega will be different, I think. And it looks like the output current is actually a sinusoid. It never goes to 0. It just
Yeah.
continues, no? Interesting.
Yeah. There is no decaying component.
There is no decaying
Because
component.
there is no e power minus at going to come
Correct.
here.
Correct. So maybe we can just write I of t
Yeah.
is so omega is root 2.
Yeah.
Oh, sorry, no, it is not.
Did I? That's what.
No, this is correct.
Oh,
We just need to multiply and divide by half. The amplitude of the sinusoid will be smaller.
okay.
So what we'll do, we'll write it in the standard form. Omega by, no, this is correct. But I think before we go to I of t, we have to write it such that numerator and this are squared.
Yeah, there should be same terms available.
Same term. So we'll write it as 1 over root 2.
Isn't?
No, not in the
Just root 2.
Yeah. Just root 2 in the numerator. And s square plus root 2 the whole square. And we'll pre-multiply by 1 over root 2 here to make sure it is the same.
Yeah. Oh.
Correct. No, this is standard form, sinusoid.
Mm-hmm.
So it looks like the amplitude of the sinusoid is also smaller,
Okay.
right? It looks like it is 1 over root 2.
Okay. So then the I of t will be 1 by root 2, the magnitude.
Magnitude. No, that is right.
Anyway, there will be this term.
Correct.
Sine
Correct.
omega is root 2
Omega is root 2. Root 2 t.
u of t.
Correct. But I think that doesn't seem right because this 1 over root 2, this seems right. Can we go to this thing, to the
Previous
circuit, previous diagram? So the frequency is correct.
Yeah.
Because half and 1.
Yeah.
Right? But the amplitude, I suspect that it the sinusoid, it should be, I think we might, let's check whether we have made a mistake somewhere. 2 by s, current is 1 by s by 2 plus 2 by s plus s, no? Correct only.
Yeah.
Okay.
I think this is correct.
This is correct. This is correct.
Yeah.
No, I'm just wondering whether we have made a mistake when we said 2 to 0. Right? Okay. So I think we have the frequency seems right.
Yeah.
The amplitude also seems right.
Yeah.
Let us just cross check on the amplitude once more. So 1 by s by 2 is 0, s square plus 2. This is right. Oh. No.
Where did we make
I
mistake?
think let me see. S squared plus 2, no?
Yeah.
S squared plus 2. This is 0. Correct. This is right. This seems right. Okay.
Maybe our students will cross check and
We'll
say,
cross check and tell
hey,
us.
man, you have made a mistake.
Correct.
So we'll leave it to them.
Yes.
But at least it's a pure sine wave. There is no
Correct. There is no decay. That is for
when
sure.
the resistor is removed.
Correct. Correct.